Hi, these are the day 7 notes for our functions unit, the locus definition of a parabola. You don't have this in your notes. I want to go through with you why is it that we need to know the other definition of a parabola or the other formulas. So far, there are actually two formulas that we use for the definition of a parabola. We have the y is equal to ax squared plus bx plus c is our standard form. And then we also know about the vertex form, y is equal to a times x minus h squared plus k, vertex form, and that's called the vertex form because we have the vertex of the parabola, it's h and k. From the standard form, we can get the axis of symmetry using negative b over 2a, and we also know that c is the y-intercept. So last chapter, we talked at length about the parabola and how to solve equations when they're written in either one of those forms. Well, there's yet another, two more equations that represent a parabola. And the reason we need to talk about those two equations is because they represent how parabolas are used in how other ways parabolas are used in the real world. Picture if you would, a satellite dish. And if you recall, satellite dishes are a U-shape, they're a parabola, and there's a reason why they're a parabola. And if any of you have the TV satellite dish, Dish Network, if you go home, you can actually see how this works. With a parabola, with a satellite dish, there is a physical feature, and in the terms of parabola, it's called the focus of the parabola. And what happens is it catches sound waves, radio waves, and what happens is these waves that come in, they come in parallel lines. They come in like this. And what's interesting is that when they hit the satellite dish, when they hit the parabola, they reflect, and they reflect towards that one particular point in the parabola. And that's where the sound gets collected. So when you look at satellite dishes, when you go home or when you drive by a house that has a dish on the roof or the side of the house, you'll notice that there is that piece of the satellite dish, not this one, we're going to erase this, that is connected to the rest of the satellite here. It's in midair, but it's anchored by the two anchors on the side, and it has to be a particular distance away from the parabola, and another line down here that we'll talk about in a couple of minutes. So if you can picture a satellite dish, and like I said, and also your dish at home, and even a contact lens, when you have video, when you're looking at something and the image comes in, it reflects from the back, and then it comes into your focal point, and when the eye doctor looks in the back of your eye, that's what he sees. So, I mean, there are a lot of things that take upon this shape. So the audio or the sound waves are coming in parallel lines, and they reflect off the back of the satellite dish, and that sound goes into this one point called the focus. So that's one way that a parabola works. The other way that a parabola works is if you think about how the headlight in the car or in a motorcycle, anywhere the flashlight is constructed. And the light bulb is situated, the light bulb is built right at and again it's called the focus of the parabola, because what happens is the light, if you're thinking about the car is over here. Here's the rest of the car. Here's the hood. Here's the headlight. There's a reflective surface, and it's usually aluminum. So the reflective surface is what has the parabolic shape. And what happens is the light emits the light, and it bounces off the reflective surface, and it goes out. And that's how the headlight works. So the light goes against the reflective surface, and it comes out in parallel lines out. So the flatter this parabola is, the wider coverage your headlights will have. And conversely, the narrower it is, the narrower the parabola is, then the more narrow your headlights are. If you think about the design of a car, some of you are thinking about driving, will be driving. You want to be able to have as much area lit at night as possible. So you want that parabolic reflective surface to be as flat as possible. But if it's if it's all the way flat, then it can't reflect. It can't reflect out where you want it to go. So it has to have some parabolic shape to it in order for the light to come in and then come back out again in the parallel lines. So the parabola comes in very handy in lots of places. Those are just two examples. In class, hopefully I'll show you a couple more examples that I'll tell you about how the focus of a parabola and other conic figures, what kind of cool thing that they have, some cool features that they have. So let's go to your notes, your day 7 notes. Locus definition of a parabola. Definition of a circle, as you know, is a collection of all points equidistant from a given point. Parabolas have a similar definition, but it's a little bit more complicated. A parabola is a collection of points equidistant from a fixed point known as the focus. And there's also a fixed line known as directrix. Now, directrix is usually below, either below a parabola, or if the parabola is on its side, like this, then the directrix is to the left of it. And we're not going to worry about the parabola on its side as much. We're just going to make sure that we all understand the happy parabolas. We may deal with the sad parabolas, but we're going to deal with the face-up parabolas for right now. So the two equations are given like this, and these are kind of weird. We have x minus h squared is equal to 4p y minus k. Or if we get y by itself, divide both sides by 4p and move over the k, we'll get y equals 1 over 4p x minus h squared plus k. Now the bottom one looks a lot like what we already know. Your y is equal to a times x minus h squared plus k, and you're right. So what ends up happening is that 1 over 4p x, a lot like, it is the value of a, meaning the steepness of our parabola. But we need that p because we need to know the distance the vertex is from the focus and the directrix. So the first thing I want to make sure you understand is when we go from vertex form to this locus definition, a is replaced by the fraction 1 over 4p. And then if we don't want the fraction 1 over 4p, if we want it to be an integer, then we have to multiply both sides by it and then bring over the k, or bring over the k first and then get rid of the 1 over 4p. I am showing you both of them because we have seen both of them on the practice regencies and on the model problems that Common Core has